Let's cover the motivation for this course called Advanced Strength of Materials. What we're trying to achieve here. Okay. So what is the goal here, right? So you have aircraft, spacecraft, and launch vehicles that need to be designed to be lightweight, low cost, and reliable. It's very amazing. If you step into an aircraft, you'll see the fuselage skin. The fuselage skin is very thin. If you look at a launch vehicle, the rocket wall is going to be very thin. So these systems have to fly. They have to be very reliable, but they also have to be very lightweight. These are complicated structures that have very complex loading conditions, and the failure modes can be quite complex. Failure modes that I'm talking about here could be buckling, it could be plasticity, it could be a lot of different failure modes that can be harmful for the launch vehicle. And so we have to have a very good understanding of the idea of stress and strain and the constitutive law to be able to understand what is going on with these systems from the structural perspective. A lot of these problems cannot be tackled from the structural perspective alone. For example, a rocket that's taking off is going to be subject to air heating environments due to the high speeds going that's going to undergo during ascent. But that heating environment also depends on the trajectory of the rocket, which also depends on other parameters such as mission design. And so as you can see, if I want to predict the structural design, if I want to predict the structural margins or want to design the system, I have to make sure that I consider these other areas of expertise so that the rocket design can work out. Now, that's from the point of view of aerospace design. The same idea can be applied to mechanical systems. It can be it can be applied to an iPhone. For example, the iPhone used to bend and used to crack. Well, you can use the idea of structural systems and structural knowledge to design a shoe for a basketball player. And that has been used by Adidas. People have used finite elements as an approach to solving problems that encompass the whole array of issues that you've seen, from civil engineering to biotechnology to heart research to aerospace design. Obviously, I come from an aerospace design background, so I'll try to apply some of those to that, but that doesn't mean we will not be applying that to other subjects as well. So when we look at from the source here, Seattle Times, there's damage that had occurred to a Boeing design, okay? And this design had a failure that occurred during ground testing. And the damage occurred at stress levels that are well below what was expected. The damage occurred on both sides of the wing body joint, so this joint right here, and the outer wing as well as the inside of the fuselage. The structural flaw in the design was significant. It set back the program a couple of years. And why I bring this up is because analysis is an important aspect of a design, just as testing is an important aspect of the design. And you may ask me, if I test, why do I analyze? If I analyze, why do I test? And the answer is, if you test, you need to analyze. And why do you need to analyze? Because I don't want to fail during a test. If I fail during a test, it will be very expensive. Number one. Number two, the testing is done on the ground. You do the testing at ultimate conditions on the ground by bending these wings as much as you can. But to be able to formulate a successful test program, you have to be able to analyze the flight conditions, because in flight, the stresses induced in the aircraft are different than in the ground. And what you want to make sure is that the stresses during flight conditions are enveloped by tests in the ground the best you can do it. Because obviously when you're testing on the ground, you cannot do it exactly when you fly it, right? The aircraft is on the ground. while when you're flying, it's not, it has no boundary conditions. The air is the boundary condition. It's surrounded by air. It's not clamped in any way. But if I can figure out a way of doing the analysis for the flight condition, I can do it for the ground condition. I can then design a test that's successful. So that's why analysis is so beneficial. But if I can analyze, why do I test? You test because analysis is not perfect. And analysis can do so much. It can, it can try to determine what the critical failure modes are, but you may not be able to capture everything. And so you want an analysis that can cover all the different failure modes, and they're validated by test. So I'll continue here. I'll continue here with the launch vehicle Falcon 9. As shown here, the sources are astronautics.com and extremetech.com. And in this case, there was an anomaly on a Dragon CRS-7. It failed close to the end of stage 1 burn, and a strut holding a helium pressurization tank broke during second stage initialization, and that caused an overpressure that caused the second stage to blow apart. That anomaly was, you could see a giant fireball, occurred while the helium was loaded into the rocket in the launch pad. That's a second failure. So this is one failure, and that's a second failure. Engineers zeroed into the design of the helium composite overwrapped pressure vessel. I have a YouTube video that goes into what a COPV is if you have interest in learning more about this topic. Not the failure, but more how to design COPVs. Why structures fails? There's a lot of reasons why structure fail. And a lot of the times it's not because people are trying to do things on purpose. Sometimes it's because engineering is hard and there are different personalities, right? I have a personality and you have a personality. Not every personality is detail oriented. For example, I am an ENTP per the Myers-Briggs scale. Well, ENTP is not detail oriented. It's going to miss some details in the calculations. But the important thing here is to understand that sometimes designs do depend upon the level of care that we put into the analysis, because errors do occur. And in this area of expertise of aerospace design, for example, we try to use something called the peer review. And I invite you to use that as you work to the various projects in your career or even at school. I invite you to work through your project and have a peer review what you've done, because that's what happens in real life. Now, during the exam, that's not going to happen. We're going to be the ones giving the feedback. So it's important then that you try your best to be careful in your calculations. The second reason why structures could fail is insufficient strength. There are situations where failure can occur below the strength of the material. And in those instances, it was due to potential misses in the failure mode, or there was some mischaracterization of the properties of that material. Another potential reason why failures could occur is that you underestimated the load. For example, a rocket that takes off, maybe somebody did a calculation, dynamic analysis, that showed that the maximum load you could see is 1.5 million pounds. But in reality, when the flight was instrumented and the telemetry was gained, it was determined that the loads were much higher. And some of the failures that have occurred in real life are because the loads were underestimated. And so that's why instrumentation during flight is quite helpful. Subtleties may not be accounted for in the design process, and you can miss a lot of different failure modes. I have several videos that go into the subtleties that could occur and can be quite problematic and can be painful, because if you miss the subtleties, then you could have a problem. As an example, galvanic corrosion is a problem. If you put, for example, a particular metal next to a composite, then if you don't realize that it's possible that this metal could corrode over time, that'll be a miss in the design process. But it's a subtlety because it's not obvious at first, right? You only know that from experience. And then why structures fail is due to unknown situations that you could not foresee, but you tried everything you can to account for it. It's just that it happened and you learn something after you do the failure investigation. And a lot of failures uh, can be classified as this last one. Another example, one example here of carelessness is that units do matter. As an example, the Mars Climate Orbiter went off course because a prime contractor had provided the navigation team with operating data in the US units rather than the SI units. And this is an error that's performed, or it occurs quite often. Unit error is an error that needs to be addressed carefully through a peer review process, particularly when there are multiple areas of expertise interacting with each other. Here's an example of an underestimation of the environment, apart from the various examples I gave earlier. Here, what you see is the famous Tacoma Narrows Bridge, which failed in November 7, 1940s. The bridge midsection here crashed into the waters, and what happened here is that the winds that were crossing the bridge produced an effect called flutter. And that happens when the wind crosses a structure and the vortices it produces has a frequency content that can match the natural frequency of the structure. And when you have the forcing function here is a wind frequency. If you have that frequency, that forcing frequency, get close to the natural frequency of the structure under consideration, then you can have a dynamic amplification, or you can have a flutter condition if it's an aeroelastic effect. In aircraft application, there is a test that is done. It's called the flutter test. They will take an airplane, Airbus A380, for example, and you can find a YouTube video of this particular test online. If you type A380 flutter test, you will see an aircraft that was going to go through the certification process was put through a flutter test, and the A380 went through a dive to gain speed so that the forces, the winds speeds were such that flutter could be induced. And that's one of the tests that A380 or any aircraft has to survive. It's called the flutter test. And so that is one way you can develop a good understanding of the envelope of the design for the aircraft perspective. Nowadays, we use wind tunnel testing as well to understand if flutter is a possibility, in addition to instrumented tests. Fatigue is another example of potential failure mode that could occur in a structural system. Fatigue is something that still occurs today, even in aircraft that you've seen flying around. Fatigue is a problem because fatigue is one of those situations where it takes cycles for the crack to initiate and to propagate, but it may propagate before the inspection is conducted. Southwest Airlines more recently has had close to 4 incidents where parts of the fuselage came off and broke off due to fatigue failure. Why does fatigue failure occur for an aircraft, as an example? So Southwest Airlines is an airline that does a lot of short flights, while the traditional model is to fly long flights. And so what occurred was that Southwest Airlines, because they're fast turnaround on the ground, will fly, and every time they flew, you have to take off from the ground to an altitude. And when you take off, the pressure inside the cabin is pressurized to about typically 5,000 to 7,000 feet, and that is done to keep the passengers comfortable. But the air outside drops in pressure as you ascend, and that causes a delta pressure across the fuselage. And because you're taking off and landing, that delta P, that pressure across the fuselage, at 30,000 feet, the pressure outside is lower, the pressure inside the fuselage is higher. That delta P causes a potential stress in the skin, as you will learn later. And that stress in the skin is going to now oscillate between taking off and landing. When I land, the pressure in the skin is 0. But when I take off, it goes up again. And so, because Southwest Airlines has a lot of takeoffs and landing in a particular day, accumulated amount will be such that a fatigue could initiate a crack, and then due to cycling loading, and then it could propagate to failure.
Was this? I don't mind if you stop it.
So why study this subject? Under applied forces, solid bodies undergo deformation and develop an internal force. The fact of the matter is, anytime you apply a force to a body of material, like an aircraft, or you apply a load to a wrench, or you apply a load to the iPhone, or you apply a load to a car by simulating a car crashing, for example. Those are external loads, and those external loads are going to get reacted by internal forces that are occurring inside of the material. And so that's why we need to study. That's why this course could be helpful to you in your career. And really, if I look at an aerospace design, but it doesn't have to be an aerospace design. It could be a building, it could be a car, it could be an electric airplane, it could be whatever design of interest. You have to understand what is the maximum expected load. Because if you don't know what is the expected load, it's going to be very hard for you to design something where the loads could be whatever. So the first step, if you're designing a diving board, for example, for a swimming pool at your home, you want to understand, okay, what are the various weights that could be experienced in the diving board you'll have at your home. And then from there, you want to understand what it takes to break it. Because if I know what it takes to break it, then I can come up with the thickness of the diving board so that it survives multiple people using that diving board to swim to your ocean, not your ocean, I'm sorry, to your swimming pool. If it's an aerospace design, such an aircraft, say you want to design a new aircraft that's unique, okay, that's special. Well, you want to know what thickness fuselage you need so that when it goes under pressurization and under bending loads and torsional loads that's going to experience during flight, that under those maximum expected loads, the stresses in the skin of the aircraft can survive the loading environments. And we use the material strength to determine whether a structure could fail. So the stress is below the strength, that's a good thing. But to really understand that for complicated systems, it's then important to understand the concept of stress, strain, constitutive law. All those three concepts need to be understood before we can actually design something. So with that said, I hope that was clear.